of log functions. So remember back to transformations. We learned about inverse functions. We actually learned for you guys that a little bit last year as well. Remember what you do when you take an inverse. What kind of transformation do you get with the graph if you take the inverse of a function? Who remembers? Yeah.
Reflection above the line y equals x.
Reflection. Oops. Reflection of each other about the line y equals x. That's what a logarithm is. It's the reflection of an exponential function over the line y equals x. So, the graph of y equals 2 to the x is shown. Okay, accurately draw the graph of its inverse. So think about things. In an exponential function, there is a horizontal asymptote. So if we take the inverse, what will be the asymptote in the inverse? Asymptote in what? If it's horizontal, then in the inverse it'll be vertical. Okay, so below we have that as our asymptote. Remember, inverses, quick way. I mean, this scale is actually good. Those are squares, so you can eyeball it, but you want to be pretty accurate. So the 0.01, when you take the inverse, becomes 1, 0. So that y-intercept becomes the x-intercept of our inverse. Makes sense from what we know about inverses. The 0.12 becomes 2, 1. Okay. 0, 1, 1, 0. Then the point, 2, 4 becomes 4, 2. Then we can think here, for x equals -1, that would be half. So -1 half becomes a half -1. And that's a decent number of points to be able to graph. Okay. And you can do the same for the one on the right. So that horizontal asymptote will then become vertical. So here 0, 1 becomes 1, 0. Here now, these points, these are easier, will go to the left. So -1, 2 becomes 2, -1. -2, 4 becomes 4, -2. And then remember 1 half becomes a half 1. So that should be enough to get a decent graph. Okay, so remember, if they're inverses, you fold your paper along y equals x if it's perfectly square grids, and those graphs should overlap each other. So the equation of the inverse is x equals 2 to the y in that one, x equals 1/2 to the y in that one. The problem is, and that's the whole goal for logarithms, is we can't isolate the y. So we have to show it like that when we're labeling. So right now, 2 more minutes, we'll go back and label it. Then it asks, are all of these functions? Yeah, vertical line test is the easiest way, right? They're all functions. Only touches once, only touches once, only touches once, only touches once. that's the inverse of y equals 2 to the x and y equals a half to the x in the form x equals. But how can we write these equations in the form y equals? To isolate y, we must bring y down from the exponent position in the equation x equals c to the y. We can do this by taking the y root. However, we would get 1. So if we take the y root of both sides, we would get that. That doesn't help us. Now we have x and y together on one side. So it really doesn't help us. Instead, we need to introduce a new function to perform this operation, the logarithmic function. So mathematicians basically define this. Okay? A logarithm represents the exponent in an exponential. So the equation x equals 2 to the y is an exponent. Sorry. Oh. However, it can also be thought of as a logarithm. For the equation x equals 2 to the y, we say that 2 raised to the exponent y has a value of x. We can also say y is the logarithm to the base 2 of x. And here's the notation. Okay? So y is equal to log of x base 2 or log to the base 2 of x. You can say it either way. Don't just say the log 2x. That kind of ambiguous what it might mean. So log of x to the base 2 or log to the base 2 of x. So the of x needs to be in there somewhere, right?
I mean, unless you're going fast and short forming it, like we all know.
Yeah, I mean, it's not as though you're always verbally saying it, right? But when I'm saying it, just be aware what it is, okay? So these two forms are called the exponential form and the logarithmic form, okay? So notice where the y is here is in the exponent, and that is the log, what the log is equal to, okay? This base is 2 of the exponent, the base of the log is 2. So no matter which form you're dealing with, the word base, okay, has the same value in both. Okay. When you're dealing with one, obviously you can have any base you want, but it would be a separate question. It's all about the base. You get it? All about the base, exponent.
Oh, I was not ready for that.
I tried to look up,
Yeah, it is a song.
in YouTube to see if, sometimes they have like parodies of exact things, right? So I looked up, and there's one teacher that did a parody of Don't Love Base, or whatever that name of the song is, and then replaced with exponent, but I felt a little bit embarrassed for her, because it was, I mean, she did a pretty good job, but like, I would never get after it, because I can't sing. So and she was a pretty good singer, but it was just like, okay, I'm not sure that kids are doing along that much.
No, I was hilarious. I love that.
Okay, so go back to your graphs and label the inverse functions with the equations in logarithmic form. So now, this is really y equals log of x base 1/2. This is really y equals log base 2 of x.
You also write it as y is negative log to the base 2 of x.
Because we have a lot of that. Yeah.
Are we supposed to insert that into our calculator?
No, you just hold on.
You can't.
Anticipation.
There's only 2 types of logs you can use.
No, you can do all of them.
Oh, really?
Yeah,
Oh,
newer versions of calculators.
You don't have to use change of base?
Okay. Listening, please. So we know that the inverse of the exponential function y equals c to the x is the log function y equals log of x basic. So inverse here, I'm just going to do my initial step, and then you don't have to, but then the log function is y equals log base 6 of x. Okay, so really that base, remember, is same base in both. But we're finding the inverse. So this log function is of the inverse. And so here, this would be y log 4/9 of x. So it's of the inverse. It's not going right from this to this. Otherwise, we have x on this, right? Because the log is the exponent. Next one is just function notation. That doesn't change anything. F of x is just y. So now y, well, here we could actually, because it's the inverse, call this F inverse. And what we'll learn in a few minutes as well is base 10 for a log is what we call a common log. It's so common that we don't have to show it. Just like a square root, we don't show the index of a 2 because it's so common. You can show it, but you don't have to. So same with log base 10, you don't have to show the 10, but everything else you do. Okay, so this is the logarithmic function of the inverse. So that means this would be x equals 7 to the y. So this would be y equals 7 to the x. And then this is in function notation. That's fine. It's just going to be x equals 3/4 to the y. So then we'll use function notation to start. Okay, you do need the brackets when you have a fraction as your base in the exponential form. You don't have to here. Please try to show some different sizes in your notation. Okay, because if you show me this, I don't know really what that is. Right?
I'll take the brackets on the x term.
Yeah, but that to me looks like maybe you're trying to say log, common log of 3x over 4. I don't know. You need to try to make that small. If you want to put brackets there, you can. If you want to put brackets there, you can. But sometimes you have to have good detail. Okay, so in general, folks at the back, for an exponential function y equals c to the x, its inverse can be written as x equals c to the y, or y equals log base c of x. Since all exponential functions have the restriction that c, the base, has to be greater than 0. Also, really, we didn't put in here, but c shouldn't be 1. I'll just put it here. Okay? So we don't want a base of 1, because then your value could be anything, right, for the exponent. And we don't want it to be negative base. Okay? So this is basically going back and forth. So since the inverse of an exponential function is also a function, you can also use function notation, which is what we did in that last chart. Okay, so here we're looking at basic logarithmic function, because tomorrow we'll get into transformations of it. So here's the graph of y equals 5 to the x. Accurately sketch the graph of log of x base 5. So remember their inverses. Very first graphs we did. This, remember your y-intercept is 1. So that means your x-intercept is also going to be 1. Unless you do some transformations on it. But if you're just taking the inverse of an exponential, then that's going to be an x-intercept of 1. Then the original 1, 5 becomes 5, 1. Okay, then think about it for x equals -1. then that would be 1/5. So this would be 1/5 negative 1/5. So your y value of your logarithmic function is your value of the exponent in your original. Okay, then do y equals log of x base 3. So that we don't have the original. So let's think about it. So I'm going to do this one in green. So my x-intercept is going to stay the same. What x value will give me a y value of 1 in here? Based on what we did here. What x value will give me a y value of 1 for log of x base 3? 3. Okay? So when these are the same, the base and the argument, we call that x value there the argument of the log. When those are the same, your y value is 1. Okay? What would x have to be to give me a y value of negative 1? Not negative 3, but I know what you're getting at.
1/3.
Yeah, you said that. Good though. So a reciprocal there, right? Because in the original, x 3 to the negative 1 is 1/3. So now 1/3 to the negative 1. And so that was 1/5. So I didn't do it very good. I'll fix this a little bit just so it's more obvious. So 1/3 would be about here. Okay, so that would be y equals log of x base 3. Okay, and then for this one, what x value will give me a y value of 1? 7. Okay, this is still going to be 1. And then, same process as the last one. If I want a y value of negative 1, this is going to have to be the reciprocal of the base, 1/7. So it's going to be sort of in here, right?
I don't like drawing radical functions, but they work like there's not the same shape. Because exponential and log functions grow / plateau way faster.
Yeah. Apparently, if you think about sunscreen, you know when it says SPF 30, SPF 10, SPF 50, that's on a logarithmic scale of one of the ingredients, whatever it is. So the difference between a 10 and a 20 SPF is bigger than between a 20 and a 30. So then there's 100. Well, if you think like SPF is 100, that's actually not that much different. So it's steeper at the beginning and then plateaus out. Apparently, I don't know what the ingredient is. I read that. Okay, so that's for C being positive. So now C being C being greater than 1. Now for C being between 0 and 1. Here's 1/5 to the x graph. So sketching the inverse of that. Okay, again, 0, 1 becomes 1, 0. Okay, and then negative 1, 5 becomes 5, negative 1. 1, 1/5 becomes 1/5, 1. Okay, so that is your y equals log 1/5 of x. Okay, that argument has to be same as the base. So when x is a third, then my y value will be 1. When x is the reciprocal of 1/3, which is 3, my y value will be -1. Or you can take graph the original, right? Y equals 1/3 to the x, so that would be -1 would be 3 here. So -1, 3 is 3, -1. You're really just doing that. And the same y-intercept. Okay, so then that's going to be and then the red, same y-intercept. 1/7 will give me a y value of 1. Okay, 7 will give me a y value of -1.
So whenever we say like we're taking a log or something, it's not like it's like an operation. It's actually the inverse of a function.
Yep, the inverse of an exponential. What's the exponent on that? It really makes it smaller.
Yeah.
The value you get is smaller than the argument.
Okay, so summary here. Y equals log of x base c. If c is greater than 1, then the shape of the graph is like this. Remember, asymptote is the y-axis. If c is between 0 and 1, asymptote is the y-axis. So do not cross over the y-axis. As you read from left to right, when c is greater than 1, the graph is increasing. And the graph gets flatter as the value of c. So what happens as the base gets bigger? So we actually did that up here. So base of 3 was green, blue was base of 5, red was base of 7. So as that c value got bigger, the graph got flatter. So the value of c increases. Okay. As you read from left to right in this case, c between 0 and 1, then this is decreasing, going down and to the right. The graph gets flatter, so let's look at these ones. The red is the flattest, okay? So let's look at the base. This is 1/3, then 1/5, then 1/7. So 1/3, 1/5, 1/7, they're decreasing in value as well. And then let's look at some properties here. So, equation, so original exponential function. The asymptote is the x-axis, y equals 0. The y-intercept is 1. There isn't an x-intercept. All real numbers for the domain, and the range y greater than 0. So we learned last week, right? Now, here, if we are looking at, this is the inverse of the exponential. The equation of the asymptote here is x equals 0. The y-intercept, there isn't one. If you look at those graphs. But the x-intercept is 1. Domain is everything greater than 0. And the range is now all real numbers. Makes sense from our knowledge of inverses. Every property of an x becomes a property of y and vice versa. Okay, so this little bit here is kind of neat, but I'm not going to spend time going through this with you. Why? Because once you draw this is a draw feature, you can't trace along, so it's not going to be really that helpful to you. And with most of you have a newer version of a calculator, and you can graph any logarithmic function really easily. You don't even have to use what we call change of base. So you can do this on your own because there's actually, I hadn't looked at the draw button on the calculator for a while. There's actually some neat features. You can draw a tangent, you can draw an inverse. You can do this if you, so this might be helpful, listen please. If say you algebraically had to find the inverse of a function, you could graph what you think it is, graph the inverse using this draw of the original, which is given to you, and make sure they overlap, right? So that would be useful. But you can't actually trace on this, it's actually just a drawing. Okay, it's not a graph. Okay, so take a look at this graph here. We've got y equals log of x base 2, y equals log of x base 10. Let's find some values, and then we'll see that we don't actually need to use the graph for these ones very often. So, first one, now, if x is 4 here in this graph, I want to look at this point where x is 4, my y value is 2. So that means log of 4 base 2 is 2. Okay. Here, same graph, when x is 8, so you look at your graph, what's the y value is 3. Okay. So this is an unmathematical way of wording what you do. So if I'm asked to do this, say I'm just asked, what's the value of log of 8 base 2? This is what I think about. So I'm asked log of 8 base 2 is equal to something. It's just an expression. I think it's down here too, right? So what do? I think, okay, I put it in exponential form. 2 to the what equals 8. How do I get that? So this is I'm mathematical. I make a little circle. Starting at the base always, I cross the equal sign, and I go back. And I call it a swoop, de-swoop. Don't know why I do it. But it kind of swoops, right? So, arrows. So 2 to the what gives you 8. Well, you got to know your powers. 2 cubed is 8. So the value of this is 3. You don't have to have a graph. Okay? So this, 10 to the what gives me 10? Well, 1. It hasn't changed. And remember, we did that on our last graph. If the argument and the base are the same, the value of that log is 1. 10 to the what gives me 1. Well, what exponent always gives you a value of 1? 0. You don't need a graph to figure that out. Alright? Or a calculator, you don't need one. Okay, so I'm going to put in my little, so here, 2 to the what gives me 8. 2. So then here, 3 to the what gives me 27. So this equals what? And there's my swoop and de-swoop. So 3 cubed. So this equals what? So 6 to the something has to give me 1 over 36. So if my base and my answer here in the exponential are reciprocals, I know that my answer needs to be negative. That's the only way you can flip something, right? Is raise it to a negative exponent. So 6 to the negative 2 equals 1 over 36. Okay? Use your brain, not always your calculator. So 16 to the what gives me 4. Well, now I'm going smaller. What kind of exponent will get a number to be smaller? A fraction, a rational, right, that's less than 1. So square root of 16 is 4. Well, square root as a power is 1/2. Okay? I just want to check something here. I want to see when I'll show you. Okay, so because most of you have newer calculators, I'll show you right now. So get out your calculator. And if you don't have a newer version of a calculator, you learn how to use your calculator on the next page. Okay? Math. Cursor up or down, but up to log base. Enter, in this case, 3. Cursor to 81. And you don't have to even use your brain. Which is sad for us not to. I'll do the next one. Map. Cursor up to log base. Fill in with 2. Fill in the argument with 128. Oh, that's 28, sorry. So map. So I think you two. Okay, so let's try though not to always use your calculator. 3 to the 4, we already got that one, right? And then that one was 7. So notice here, right away I know that's going to be negative because my base is 2 and my argument is a fraction, 1 over. I know 2 to the 5th is 32, so this is going to be negative 5. 16, now it's a fraction, so I know that's going to be negative as well. But 4 is smaller than 16. So remember, the square root of 16 is 4, so this is going to be negative 1/2. If these are the same, it's 1. If this is 1, the value is 0. And this one, do I need to go 9 to the 6th in my calculator? No, because this is saying 9 to the something equals 9 to the 6th. Well, hello, 6. Okay? So sometimes students make it way harder than it is. If that base is the same as the base in the argument, then the value is just the exponent on that.
Algebraically, you can say that. Same as if you have a base raised to the logarithm with that base. So if you had like 9 to the power of log base 9, that cancels out.
Okay, so these are just those sort of common properties. Base is the same as the argument, answer is 1. Argument is 1, answer is 0. Argument, the base of the argument and the base of the log are the same. Is that an x there? Yeah, it's whatever the exponent is. Okay. Oh, I missed this one, sorry. This one here, so you're thinking 4/3 to the something equals 81 over 256. Well, first of all, I can't raise 4 to something to get 81. But I can raise 4 to something to get 256 and 3 to something to get 81. So that tells me I've got to take the reciprocal, right? That exponent has to be negative. And then I know 3 to the 4th is 81. And just check, is 4 to the 4th 256? If it didn't work out, then there would be integer value for that. Okay, so previously we saw the equation x equals 2 to the x, 2 to the y is equivalent to y equals log of x base 2. Use this to complete the table by finding the equivalent form. So exponential form, so basically we're now putting the exponent is 5 equals log base 4 of 1024. Okay. So that's the exponent, that's your log value of your exponent. It's your value of your log. This is the argument, this is the value of the exponent, exponential, the bases are the same. You can punch in log of 1024 base 4, and you'll get 5 on your calculator. So now my swoop is swoop. So 5 squared equals 25.
Here's my question. Why is it called a logarithm?
That I have some dentistry. Move the log down the hill.
And if I'm like,
Oh,
the rhythm that wasn't like increased, like you got, oh, this rhythm is too short. 1/8, 1/16, 1/16. That follows the binary law. Yo.
So from here, again, you can do your little arrows. So 1/2 is your base. Value of the log is your exponent equals 26.
I gotta do some Hey, good. I got those. Time management.
Okay, so here again, graphs are given to you. This is your log base 3, this is your log base 7. You're asked to solve for x here. So think about it. We're trying to find the log of a number, base 3, that gives us a value of 2. This is where I use I don't need a graph, right? So this is saying I can look at the graph. So what x value gives me y value of 2? Looks like 9. Okay? Let's think about it. 3 squared equals 9. Okay, my sweet. So base across the equal sign, squared equals x. So here, 3 to the 1 gives me x, which is just 3. So then look on when y is 1, what's x? It's 3. When y is 0, what's x? It's 1. Because 7 to the 0 is 1. Okay? Again, you don't have to have your calculator. So, log of 9 base 3 is 2. 3 squared is 9. An estimate for log of 10 base 3. So look at it here. So X was 9, okay, so the value of the log was 2. Now if X is 10, the value of the log will be a little bit more than 2. Maybe 2.1, okay, you're just estimating. On your calculator, if you have that capability, most of you do, then you would just go math up to log base. Oops, right? 3, 10. Well, it rounds to 2.1, so pretty good. Okay. Okay, so it says use the results from number 14 to help solve the following equations. Number 14. I guess you could use, for some of these, you can use that graph, but it's really the process that we learned from number 14, not necessarily the graphs. So again, 3 to the 4th gives you x, so x equals 3 to the 4th. Practice your mental math. Get ready for next semester.
Although, like, yeah, I mean, these are pretty easy numbers. You're not going to be like, what's 17.0893 to the power of pi? You're just like, calculate that mentally. It's like, I. Oh, there are, like, you can do that, but like, well, dude, I don't even know 20 decimals of pi. That's pretty good. I mean, 22 over 7 is already a pretty good approximation, and it's not even that good.
Okay, now what about this? We'll do these solving some log equations that are more complicated, which all this is 2 has been added to x. Still the same deal, right? So now, 3 to the 0 equals x plus 2. I like to show x's on the left, but it doesn't matter where you show it. Okay, so x plus 2, well, 3 to the 0 is 1, so x equals negative 1. Okay, so work through those. So, if your equation, if you're solving an equation that says x squared equals 25, remember there's 2 possible answers. There's positive or negative 5. But that wasn't our original equation. Our original was log of 25 base x. Remember, our c value has to be positive. So this, we have to eliminate that from our solution set. Okay? Yep.
I can't see positive, negative again.
Try graphing it.
Because you can't, has to be true for all real numbers, right? So if you have a negative, in order to get, this will always be positive as well. So you can never take a negative base and make it, sometimes you can make it positive, but not for all real numbers. This has to be all real numbers, right? The value. So if we had an odd value here, then x cubed equals 125. If that was negative, that wouldn't work, right? It wouldn't give you a positive. Same thing is if you're going backwards, you can't take the base to be negative because maybe you're taking the square root of it. You're raising it to the 1/2. So maybe this is 1/2 here. And negative to 1/2 doesn't work, right? Imagine it.
Or if you have, like, for example, yeah, like.
Let's think about the graph, right? Your domain for that logarithmic graph is x greater than 0.
Also, like, think about this. If you have,
Oh,
like,
but that's the graph. You're asking about the base. So, but just remember the base and the x value have to be positive.
like, if you don't have, like, a whole number, how do you, like, if you have a negative to not a whole number, how do you determine what that's going to look like? Right? Because, if you multiply the same number together negative 3 times, you get a negative number. How do you multiply a number together 1.5 times?
Well, that's a graph. So
Yeah.
you can't do that.
Well, real number.
Not going too far, that would be 40, right? So you can't do that.
Well, unless we do. I'm just not going to get it. Not yet.
Not yet. Okay. So then we square both sides. Okay, so you don't have to worry about that one. If that was x to the 1/2. It's going to be positive, not positive or negative. Okay, so then this one, remember we were solving some of these the other day. So now 16 to the 3/2. So that's the square root of 16 is 4, cubed is 64. But if you're taking the square root of 16, it could be positive or negative, if that was your question to start. But this is coming from a logarithmic function. So I have to eliminate the negative. I can't have a negative as the base. Okay? So I'm only going to choose positive 16. Okay, so on your calculator, folks, so on your calculator, you'll also notice a log button. So when we were doing logs with a different base, we went through math key. Now we go to the log key. It just shows up as log. Okay, it doesn't have any option to put another base in there. So log of 10, what does it give you? It gives you 1. Okay, so go through these. Log of 100 is 2. What do you think log of 1,000 will be? 3. Okay, so those patterns, this is kind of like inductive reasoning, right? We're looking at specific cases to come up with a statement. Well, that means that if we get an answer of 1, what we talked about before is the base and the argument have to be the same. So that means the base is 10. Well, check it. 10 squared, yep, that's 100. 10 cubed, yep, that's 1,000. So this here should be, it's a fraction, so it should be negative. Negative 3. Okay? So that log button on your calculator is for just base 10. Okay? So anything you're doing with base 10, just use the button that's right there. This is also a logarithmic button, LN. It's called a natural logarithm, and you'll learn more about that in calculus.
Base
Okay.
E.
Base E. I don't think we talked much about it.
Is it like, is that the only, like, e to the x not that function where the derivative is equal to its
Exactly.
right?
So, the base of each of the logs, folks, too much talking. The base of the log is not explicitly stated. Based on the results, the 5 base is 10. Logs of base 10 are called common logarithms, okay, because they're very common. We can use the graphing calculator and common logs to evaluate logs with bases other than 10. So this, for those of you that don't, Kristen, so you got to follow along in this part, that don't have that opportunity to do a different base. Let's see how it works. Everyone needs to notice this change of base, though. The formula is on your formula sheet. You'll need to end up using it when we're proving log statements or solving log statements. So just because you have a newer version of a calculator doesn't mean you don't have to know this. So want you to, so let's say we are asked to do this. And let's say you just had a regular scientific calculator that just had log, like this one. I want you to enter this into your calculator. So don't answer that right away. Well, I guess you could, but let's do it. Log of 16. Don't forget to close the brackets. Divided by log of 4. Okay, we get 2. Okay, and we should actually know that one in our head. 4 squared is 16, so you can do that. What do you notice? They are equal. Okay, let's try the next one. Log base 10 of 81 divided by log base 3. Log of 3 base 10. So log 81, close the bracket, divided by log 3. Okay, you get 4. 3 to the 4th is 81. So take a look at what this is in terms of common logs. This is log base 10 of 81, the original argument. This is log base 10 of 3, the original base. 16 is the original argument, 4 is the original base. So we can use a graphing calculator to evaluate this by taking log of B over log of C. New base is 10. Doesn't have to be base 10. We could have, if we had a separate key that was base 3, we could still do this. These bases just have to be the same. So we're really, that's why it's called the change of base formula. We're going from a base of C, and now we're using expressions with a base of 10, or it could be a base of 300. It doesn't matter. We're changing the base as long as they're consistent. And this is your original argument, and your original base is now the argument of your denominator. Okay, and as I said, we'll end up using this when we're doing some solving and proving and simplifying too later this week. Okay. So, evaluate without. So here, we can figure out, so we don't need a graphing calculator. 2 to the 500, 2 to the something has to give us 512. See if you can do that without a calculator. 2 to the 9. Right, so 64, so 16 times 16 is 256, right? So 4 and 4 is 8. 256 doubled is 5. So that's going to be 9. 2 to the 6 is 64. That reduces. Okay. What's log of 512? Base 8. 3. Okay. 8 times 8 is 64. Times 8 again is 512. 8 squared is 64. Okay, so those were, we just changed the base of those. What do you notice? They're the same. Here, log 512, common log, divided by log of 64, 1.5, which is 3 over 2. Okay, so what do you think log of 512 over base 13 over log of 64 base 13 will be? 3 over 2. Okay, so we just changed the base. These bases were consistent within each, but the same arguments and the bases were the same within it. So this I will put into 3 over 2. Okay, so this is on your formula sheet. It's called the change of base formula. And as I said, it's going to be useful particularly, well, for those that don't have the capability in their calculator to do a different base, as well as when you get to solving and other properties. Okay, so let's work backwards from that. So notice how this is same base, okay? Says evaluate by expressing it as a single log. So when we have a fraction, so a division of logs, guys, we cannot just divide the arguments. Okay, it doesn't work. But going backwards here, notice what happens. That argument in the numerator is the argument of our single log. This argument in the denominator is the base of our single log. Okay. And we can evaluate that, right? 3, well, actually, you can't check that one in your head because 64 is 3 to the sum. Okay. So we express that, and then 4 cubed is 64. So separately, I can't do that in my head. I don't know what the answer is to that part or this part. But if I change the base, then I can evaluate it in my head. So now let's express it as a quotient of logs with base 2. So I could do this as log of 64 base 2 over log of 4 base 2. Okay, and again, I can check that one. 2 to the 6 is 64. 2 squared is 4 equals 3. What is going on back there? Okay, and then express as a quotient of common log. So this would be, for those of you that don't have the opportunity to do another base on your calculator, let's say. And if you check that on your calculator, so evaluate log of 32 base 8 without the aid of a calculator. So what hint is, what base would make it easy? So look at 8 and look at 32. What base is good to use for both of those? 2, right? So I would show this as log of 32 base 2 over log of 8 base 2. To the fifth is 32. 2 cubed is 8. think you might be able to do that without converting it. If you think about 8 to the something equals 32, you know you have to take the cube root of 8 and then raise it to the exponent 5, so that would be 5/3. Calculator, the fastest way to do this with a calculator would actually be to go log of 32 over log of 8, because doing this requires you to go in and do that log base, right, which is an extra couple of keystrokes. So the fastest here would be log of 32 divided by log of 8. Okay, and then you can even do math graph if you want to convert it. Okay. So, let's just do 22 and then we'll call it a day. Okay, evaluate these without the use of the calculator. So that's a common logarithm. So 10 to the 1 gives you 100 is 2. 49, so you can do 49 to the something equals 7. Well, we've got to take the square root, right? Just remember, 7 is square root of 49. As an exponent, square root is 1/2. Okay, 9 to the what gives you 27. So that one, you're going to have to do a square root and then cubing, right? So that's 3 over 2. This one you might want to show with a new base. Base 3. So that's going to be 3 over 2. You don't have to do it like that. You can think about, oh, okay, I've got to take the square root of 9 and then cube it to get 27. Then think about square root is 1/2, cubing multiplied by 3, so 3 over 2. And then same thing here. Maybe you want to think about, okay, this is the same log base 3 of 27 over log base 3 of 1/9. So that's going to be 3. This is going to be a negative, right? Because that's a fraction. That's going to be negative 2. So overall, it's negative 3 over 2. Take a look. This was the reciprocal of this. Argument was the same, so it makes sense that those are opposite in sign. Okay, so this one, find the exact to 4 decimal places. Evaluate with the use of a calculator, round to the nearest 10. This will be change of base for some of you. Others, you can just enter it in your calculator. It's not really a big deal. This one was talking about that draw graph. So here, you can all enter this, so you don't really need that draw graph, except for Kristen. You would have to use change of base, that's all. Okay? And that's it.